I'm going to briefly demonstrate how to use an interactive simulation that models a solid liquid phase diagram, and in particular, how the lever rule is used to essentially apply mass balances to determine the amounts of each phase in equilibrium. So, if we look at a snapshot of the simulation, we have this black dot whose location is changed by changing the temperature and by changing the fraction of uranium. And then on the right side, we have a bar graph that shows for this particular location, here's the mole fraction of this liquid phase. And then it's in equilibrium with this compound. And the compound, its mole fraction is shown in the diagram here. So we can move the point around by moving these sliders, and we can see different phases in equilibrium. So we can move the point around with these sliders, and we see which phase of equilibrium. If we're up here, we have all liquid phase. Down here, we have liquid in equilibrium with the solid, and then here we have two solids in equilibrium. Notice that this shows dashed lines here where this distance is pink, corresponding to this point. This is green, corresponding to this point. And the reason is that as this pink gets longer, in other words, if we move this black dot to the left, pink gets longer, we have more of this liquid phase. We're closer to the liquid phase, so that distance is longer. And the lever rule says that the amounts of these two phases are proportional. So the amount of this liquid compared to the amount of this compound is equal to the ratio of this length over this length. So the length far away from the phase, from liquid phase, as it gets longer, we have more liquid phase. It's not surprising as we're moving this to left. And so the lever rule is the same as calculating mass balances. So let's look at this simulation. So in the simulation, we have directions that briefly describe how to use the simulation. Here are details which essentially show how the lever rule is related to amounts of each phase. And as we move uranium mole fraction until we get to this point where we have almost all of the solid phase. Now we're in equilibrium with the liquid that's a different composition. That's the liquid right here. If I were to lower the temperature, now we have two solid phases in equilibrium, a pure uranium solid and this compound. Again, if I move over to here, and then let's lower the temperature. Again, we have two solids. Now it's the pure titanium phase in equilibrium with the titanium-uranium compound. So moving around, the simulation calculates how much of each phase. When it's liquid phase, such as when I raise the temperature, so we have some liquid phase, they'll give the composition of the liquid phase.